Right, so in a previous video we looked at the magnetic field that was generated by a current carrying wire. So if we have a wire, for example this orange wire here, carrying current I, okay, in that direction, it's going to be generating a magnetic field. Okay, how do we figure out the direction of the magnetic field? Well, we used the right-hand grip rule. So the right-hand grip rule looks sort of like a thumbs up, where you point your thumb in the direction of the current, and then the magnetic field points in the direction of your fingers, and that magnetic field will form concentric circles around the wire. Okay, now if I was to take this wire that's generating a magnetic field and place it into a different magnetic field, then the two magnetic fields will interact with each other. So the magnetic field of the wire will interact with the magnetic field of the other magnetic field. Okay, so for example, if I take this wire and I place it here between these two magnets here, the two magnetic fields are going to interact. Okay, so that wire, that orange wire, will therefore experience a force. Okay, and that force we can figure out if the wire is at 90 degrees to the magnetic field that it's in, then that force can be calculated using this equation, where we've got F force is equal to B, which is the magnetic flux density. That's basically just how strong the magnetic field is. Okay, you know that if there were more magnetic flux lines, these grey lines here, more of those magnetic flux lines packed together, more closely, more densely packed, then that's going to give you a larger magnetic flux density. That's going to give you a larger magnetic field. Okay, so F equals B, magnetic flux density, times by the current carried by the wire, times by the length of the wire. Okay, so F equals BIL. F equals force is equal to the magnetic flux density times by the current times by the length of the wire. Okay, so force in newtons, magnetic flux density, and the magnetic flux density is measured in a unit called Teslas, which we represent with a capital T. I is current, measured in amps of course, and L is length, which is in meters. Okay, right, this, I'll mention it again, this formula only works if the wire is at 90 degrees to the field. Okay, if the wire was at any other angle, then it will experience a smaller amount of force. Okay, it will still experience a force unless it was at 0 degrees to the field. In other words, if the wire was parallel to the field, so if the wire was parallel to the field like this, then it would not experience a force. Okay, so the wire can only experience a force if it is at some angle to the field. If it's at 90 degrees to the field, we can use this formula. So we've worked out the force. How do we figure out the direction? So we can use Fleming's left-hand rule. Okay, so what is Fleming's left-hand rule? Well, Fleming's left-hand rule looks a little bit like this. If you take your hand, your left hand, you put your thumb up, you put your first finger pointing outwards, and you put your middle finger at 90 degrees to both of those, pointing towards you. Okay, the first finger is going to represent the direction that the force is going to act. Okay, so this is our force thumb. The first finger is the direction of the magnetic field. Okay, from north to south. The middle finger is current. Okay, so that's conventional current then. So force field current. So let's figure out then the direction of the force. So firstly, let's put our first finger in the direction of the field, from north to south. Now the middle finger in the direction of the current is pointing in the direction of the current, and your thumb is pointing upwards. So this wire will experience a force upwards. Okay, right. So you can use this equation to work out the magnitude of the force, and then you can use the left-hand rule to figure out the direction of that force. Okay, right. Have a go then at this question here. Okay, so you've got a 20 centimeter length of wire. It's got 2 amps of current flowing through it, and it is placed in a magnetic field of flux density 0.5 Teslas. Just figure out the strength and the direction of the force acting on the wire. Pause the video, have a go at it. Unpause when you're ready for me to go through it. Okay, so firstly we're going to use F equals BIL to calculate the force on the wire. Okay, so the force is given by B, magnetic flux density, which is 0.5. Multiply that by the current, which is 2 amps. Multiply that by the length, which is 0.2 meters. You get 0.5 times by 2, which is 1. Multiply that by 0.2. You get 0.2 newtons of force. Okay, now using the left hand rule, you're going to point your first finger in the direction of the field. Okay, so your first finger will be pointing in this direction. Okay, then you're going to point your middle finger in the direction of the current. So your middle finger is pointing this way. Okay, and you should find that your thumb is pointing directly downwards. Okay, so you'll have a force of 0.2 newtons acting downwards. Okay, we'll have a look in the next video at electric motors, where we'll be using this again to have a look at electric motors. Okay, I'll see you then.